To prove the permutation problem, a permutation lower bound, we look at the following concept. We would like to define the state of a disk. The state of the disk is defined by the permutation that is on the disk, while ignoring the order in each block. To be precise, two different permutations S1 and S2 of the same elements are in the same state if by permuting the elements in the blocks of one of them we can turn it into the other one. Now I would assume there is S1 here. If I can permute the elements in each one of these blocks without moving the elements from one block to another block, just permute the element in each one of the blocks. If I can do this, and if I can turn S1 into the permutation S2, then we say they are in the same state. To be able to prove the lower bound, we need to count how many different states exist among all the possible inputs. So obviously the number of different permutations that can be created from n elements is n factorial. However, the number of states is less than that because many permutations could actually be in the same state. To be able to count the number of states, we need to count the number of permutations that can have the same state as a fixed permutation pi. So assume I have a permutation pi and I want to count the number of permutations with the same state. In other words, I would like to know in how many different ways I can shuffle the elements in the blocks of pi. So for every block, for example this block, there are b elements in the block. I could shuffle them in b factorial different ways. For the next block, I can again shuffle the elements in the block in b factorial different ways. So for each one of those blocks, I have b factorial different choices. So that means the total number of choices I have is b factorial to the n over b. So this means this is the number of permutations that have the same state as pi. Since the total number of permutations is n factorial divided by this term gives a bound on the number of different states that I have in my problem. Okay, so how does the permutation lower bound works? Observe that at the beginning I have one fixed input that is in one fixed state, and I would like to reach all possible permutations using this state. In other words, the output, the algorithm could ask for any of the this many states to be created by the end of it. So I have one starting state, and I would like to potentially reach this many different states depending on what the algorithm and what the problem asks me to do. To be able to prove a lower bound, we simply need to count how many different states I can create starting from one state. So assume I have this one state at the beginning, and I have a budget of one read and one write. And I would like to know how many different states I could create using this budget of one read and one write. To be able to read a block, I will just simply have the number, I need to have the number of the block. So for which block to read, I have n choices. Now inside the main memory, I have m elements, and I would like to choose b elements to write. Since the order of the elements in the block that I'm writing does not matter, this is the total number of different ways that I can choose b elements out of m elements. And once I have chosen this b elements to be written in one block, I could write them in any of these positions and in any of the blocks. So there are n different places that I could place this block. So that means the total number of states that I can reach with one read and one write is at most this much. Easily we can see that if I have k reads and k writes, I could reach at most this many states, because for every state that I have here, I have k minus 1 different states, and by simple induction it follows that this is the number of states that I can reach with k writes and k reads. So obviously the number of states that I can reach must be larger than the number of states that I must reach. So in the worst case, the value k should be such that this right-hand side, the left-hand side, is bigger than the right-hand side. And now we just need to do some math. From the previous video, remember that I have the following equalities. The natural logarithm of n factorial can be written as n log n minus O of n. And m choose b can be written as essentially theta of small m to the power b. With these two formulas, it is relatively easy to resolve and solve for k. I take the natural logarithms of both sides. I get to this inequality. This inequality can be simplified in the following way, where I expand, and now So I multiply n inside this parenthesis, I get capital N plus O of capital N here. N log n minus n log b turns out to be n of log of n over b, and then minus O of n plus O of n can be bounded, can be lower bounded by this term. So I must have that again the left hand side should be bigger than the right hand side. And now observe that this left hand side is upper bounded by this new term. This is because a plus b is less than equal 2 times max of a and b. Okay, so here I factor k out, and I have the factor 2 here, and then inside here I have a, which is 2 times ln of n, and b, which is this parameter. Okay, so this left hand side is bigger than this side, which is supposed to be bigger than this side, so I must have this equality. And now I can basically solve for k. I can say that k is bigger than equal this thing divided by this thing. Since I'm dividing by max turns into a min, and I have two cases. Either I divide by ln of n, or I divide by this factor. If I'm dividing by ln of n divided by ln of n gives me capital N, and n ln of n divided by this term gives me exactly this amount that I wanted to prove.